Hi friends, I am your Karthik Kate and this is Kate Tutorials. So in this video, we shall discuss one more alkaloid, that is lysergic acid, right? So this lysergic acid is nothing but optically active alkaloid it is. So it is called as D-lysergic acid or plus lysergic acid. So these are the other name of this lysergic acid, right? So here we can LA stands for lysergic acid. Now onwards, if I write LA, you should understand that is lysergic acid. So D means dextrorotatory or plus means dextrorotatory. It rotates the plane polarized right towards right side. So that is called dextrorotatory. So this it means this lysergic acid is optically active. Optically active. Right. So then once we got this, it is optically active. So this lysergic acid, if you see the structure in the upcoming videos, there you will get that it will be having two chiral carbon, because of which it will exhibit this optical activity, right? And this lysergic acid is a ergoline alkaloid, means this lysergic acid will get from ergot fungus. So ergot is a fungus from which we will get lysergic acid. So this lysergic acid will be present in the form of seeds. So within the seeds we will extract this lysergic acid, right? So it is famously called as LSD, right? So LSD drug, you have heard about LSD, right? LSD stickers in Sanju film, if you see, he used to attach that sticker on within this mouth, right? So below the tongue he used to put this LSD stickers, right? So these are drugs, right? So these have got so many medical importance, but people will misuse it, right? So that is the LSD. So what is this LSD? LSD is nothing but lysergic acid amide derivative. Amide, that is simply nothing but amides of La, means amides of lysergic acid is nothing but LSD. So if you I will give you the structure of lysergic acid, then I will form the amides of it, you will get the structure of LSD. That we shall see in the upcoming videos, right? So this is all the introduction to this lysergic acid. Now it's time for its structure elucidation. So the scientists, what they did, they took this lysergic acid, right? So they treated this lysergic acid with one equivalent of CH3I. One equivalent of CH3I. So they found only one equivalent of quaternary ammonium salt they got, right? So it means that this lysergic acid has got one nitrogen which is tertiary, right? But for molecular formula determination and everything they determined, they saw that this lysergic acid has got two nitrogen. Two nitrogens are there in lysergic acid. Within one is tertiary, and the nature of second nitrogen, they saw that it consumed two equivalent of CH3I. It means, see, that nitrogen is there, right? So it has attached to this hydrogen. It is like that. So when we treated with one equivalent of CH3I, so it formed like this CH3. So it formed tertiary nitrogen. Further, it consumed one more equivalent of CH3I, tertiary iodide, methyl iodide. So it formed now quaternary salt like this. Now it formed this. So it means that this nitrogen should be secondary, because once it consumes one molecule of CH3I, it formed tertiary amine. Further, it formed this quaternary amine. So this nitrogen is secondary, right? So what they concluded? So this lysergic acid has got two nitrogens, in which one nitrogen is tertiary because it directly formed quaternary ammonium salt, and the second nitrogen is secondary because it consumed two equivalent of CH3I, one equivalent and second equivalent to form this quaternary ammonium salt, right? So from that they gave the conclusion for this two nitrogen. Once they gave the conclusion for these two nitrogen, further what they did is, see here, further what they did, they started for this structure. So what is the structure of now lysergic acid? So the second thing, so once they gave the conclusion for two nitrogens, the titration experiment they did, that is acid base reaction you can call, or neutralization reaction. Acid base reaction is also called as neutralization, right? So these things we have studied. So or sometimes these are called as titration experiments. So what is this titration experiments? So what they will do, so they took this lysergic acid and they treated with a base, so it consumed only one equivalent of OH minus. So they concluded that this lysergic acid has got one equivalent of COOH group, right? So because of the presence of this acid group, so it is called as lysergic acid. So they concluded that this lysergic acid has got one COOH functional group, right? That is the acid, carboxylic acid group it has got. Once they understood this from this titration experiment, then what they did, they took this lysergic acid. To that they added this reducing agent. What it is? Sodium. It will give the electron, because it is metal are good in giving electron. It will form Na plus one electron it will give. In presence of protic solvent like methanol, protic solvent means this will give H plus, whereas this sodium will give electron, like this reaction. So these act as a reducing agent, right? So when they saw that, they observed that this lysergic acid will consume 2 H plus, like this, one hydrogen here, one hydrogen here. So they concluded that this lysergic acid is the right. So this lysergic acid will be having double bond. So when they treat with this any reducing agent, it will be single bond. That is, the unsaturated bond becomes saturated. So it consumes 2 hydrogen. So they concluded that this lysergic acid will have double bond. So first conclusion it is, this is second conclusion, and third conclusion is the lysergic acid has double bond, like this, double bond, right? So this is the third conclusion. And the fourth conclusion, before going to this fourth conclusion, they conducted one reaction. From that they could able to tell the structure of lysergic acid. What they did, they took this lysergic acid, to that they treated with KOH and they heated, that is KOH fusion reaction they formed, and they got this product. What is this? This is nothing but our indole. They got this indole skeleton like this. So here CH3, here CH3, and this is the indole skeleton. So since they got this indole skeleton, so one thing they concluded. So initially they knew that it has 2 nitrogen. Within that, one nitrogen is secondary. If you see this nitrogen is secondary, because it is attached to only 2R group, and the other one is hydrogen, right? So they got for this one nitrogen, right? And also for molecular formula, everything, they understood that the lysergic acid will have this indole skeleton, right? So they came up with this structure. So they thought that this lysergic acid will have this indole skeleton like this, right? So indole skeleton it has got, and this indole skeleton is there, and this indole skeleton from other remaining carbons are there, right? They concluded that 1, 2, 3, this is 4. So it will form 6-membered ring like this. 1, 2, 3, 4, 5, 6, right? So it will be like this, right? In which so they got this one nitrogen. Now they have to tell for position of COH and the position of one more nitrogen, which is tertiary. Tertiary means it is attached to like this CH3, right? So this is tertiary. They have to give the position of COH and nitrogen, and these rings they gave based on hydrogen deficiency index, that I have told you, hydrogen deficiency index, HDI we call. From that we can tell that whether ring is there or double bond is there based on the number of carbon remaining and the hydrogen, right? So from the molecular formula, once they got this as a thing, The other thing, they will we can guess by our knowledge, we can guess whether both are ring or not, because the number of carbon if you count and number of hydrogens, then we can arrange somehow, and we can we can have a rough idea that this lysergic acid will have this skeleton only, right? And further they saw few more reactions. From that they concluded that this COH group is there on this position only, and this tertiary nitrogen there on that position only. That we shall see now, right? So this they understood. So what they did, they took this only simple indole, right? So this is the basic skeleton they got now. So they took simple indole. They took this indole, and what they did, they did this UV spectroscopy on this indole, and they observed it to be 275 nanometer, right? And they took this lysergic acid, and they did this UV spectroscopy, and it was observed at 310 nanometer, right? So what they concluded? So they concluded that initially we saw that this lysergic acid is having two double bond, because it consumes hydrogen, here on hydrogen, here on hydrogen, one equivalent of H2 I can tell, right? So they knew that this lysergic acid has got double bond, right? So here if you see indole, it is simply 275, but 310 means it is in conjugation, the double bond is in conjugation with this indole skeleton. So later they found out that, so here it is double bond, single bond, double bond, the double bond is here only, they concluded, right? Why they concluded? Because for indole it is 275 nanometer, since 310 means it is in conjugation, and we know that, see here, if I have right, so this is what, this is my simple alkene. If you see its nanometer, it will be around 175 nanometer, right? If I take this 1,3-butadiene like this, because of conjugation what happens, the energy decreases. As energy decreases, this nanometer means wavelength will increase. If you see its UV spectroscopy, you will observe it as 270 nanometer. So what you have understood, as conjugation increases, energy decreases, so wavelength increases. That you will study in UV spectroscopy, right? So here no conjugation, so energy is more, so wavelength will be less, because energy and wavelength are inversely proportional, right? So more energy, less wavelength, less energy, more wavelength. As conjugation increases, the wave number is not wave number, here it is wavelength will increase like this, because energy will decrease here. It is more, it is less energy, right? So this is the thing. So they concluded that this double bond, the position of double bond is like this only, because unless it is like here, if it, you will tell double bond can be here or here, but the thing is 310 nanometer, it is only possible when it is in conjugation with any of the pi bond. So here it is pi bond, so pi bond, single bond, pi bond. So here it is conjugation is there, because of which they gave the position of this pi bond, right? So they got this skeleton now. Further, to tell the position of COH and one more position of nitrogen which is tertiary, what they did one experiment. That is, they took this lysergic acid it is, so they treated this lysergic acid to a base OH minus, and they found that this lysergic acid was converting into lysergic acid, right? So these ergot alkaloids are there, right? This lysergic acid is a ergot alkaloid. This ergot alkaloid will be in two form. One will be like lysergic acid, and it will be having one more isomer, that is isolysergic acid. Every ergot alkaloid will be present in like two forms only, two isomers, right? So when they treated this lysergic acid with OH minus, they used to get this isolysergic acid. Similarly, this lysergic acid in presence of OH minus, it used to give this lysergic acid. It means it will be in equilibrium like this in presence of base. So because of this reaction, they got that COH group will be like this only. See here. So they gave this structure. Let me take one more chalk piece. So they gave this structure. See, Initially till now they have got this structure, right? Now they gave this structure. One of the nitrogen which is tertiary will be here, which is attached to CH3, and this nitrogen is secondary, and here conjugation will be like this, and double bond will be here, and this COH group will be like this, COOH, right? So here if the stereochemistry is above, then we call it as lysergic acid, La. When we treat with this OH minus, we will get isolysergic acid. The structure of isolysergic acid, now we will get it. Why we get there only? See, if this COH is above, then here this hydrogen present at the same carbon will be below here like this. Alright. So what happens? This OH minus is there, right? So it will take this proton. Why this proton will be taken? Because this is COH group. This is alpha carbon. So alpha carbon having hydrogen, we call it as alpha hydrogen. Alpha hydrogen will be acidic. Once it takes this H plus, this electron density goes to this carbon-carbon bond, and this pi bond comes on oxygen, right? So this is the thing. So what we will get? We will get this thing. See here. Now I placed the COH group and NH2 group here only because of this reaction. So what we got? We got this thing, right? Every time I should not draw all those things, otherwise it becomes confusion. Later I will just see here what happens. Just you see the structure now. Here it is CH3. Now what happened? I got here double bond here, right? At this carbon here I have OH, O minus, and here I have OH, right? And this H plus and OH minus, it formed water. Right, so here I have double bond now, right? So this H plus can come here also. OH, O minus, instead of writing O minus, I can write OH here, right? So it is C double bond O minus. Now what happens? This electron density as comes here. Now see, it is what? C double bond C. C double bond C means both the carbon are sp2. sp2 means both carbon are planar like this, right? So both carbon are planar like this. Initially what happened? This COH group was above and this H group is below. But as soon as now electron density comes here back like this, as electron density comes here and this electron density comes on nitrogen, now instead of this hydrogen attacking from below, it will attack from above, right? So possibilities are there, both the possibility. But now if I do like this, other like this will be continued here. This structure you can write by yourself. Now what happens? See, this C double bond O, we got this OH is there on as it is, but here as soon as this electron density comes here, this hydrogen will attack from above, so this COH group will go below and other things remains as it is, right? So what you understood? So we understood that initially it was lysergic acid in which the COH group was above and H was below at this carbon. Later they found out that in presence of this base OH minus, it will undergo like this tautomerism, because of which this COH group will go below and H will come above. Why it happened you should understand, because it is planar. Once it is planar, as soon as this electron density comes here, right, this hydrogen can attack from above or hydrogen can attack from below, right? If hydrogen attacks from above, we will get this isolysergic acid. If hydrogen attacks from below, we will get this lysergic acid. So it will be in equilibrium, right? So we will get 50% of lysergic acid and 50% of isolysergic acid. So this is the thing you should understand, right? So this happens only when this tautomerism happens. That tautomerism happens in presence of base only, because this proton is acidic as it is alpha proton. Means alpha hydrogen present on alpha carbon will be acidic, because this is the electron withdrawing group, that is acid group, right? So these things you know, right? So other things will be as it is. So because of this reaction in which lysergic acid converts to isolysergic acid in presence of base, they gave the position of COH group, right? And how you will ask, how did they give the position of NCH3, right? This tertiary nitrogen position. That I will explain it now, right? So how did they give the position of this nitrogen is, they did one more experiment. From that they gave this position, right? I hope you got the structure of lysergic acid now. So lysergic acid is the structure like this. So one more thing before going further, I have to explain it. The numbering will be like this: nitrogen 1, this carbon 2, 3, 4, 5, this nitrogen 6, this is 7, 8, and this is 9, and this carbon is 10. Right. So what are the things we observe? This C5 is there, right? C5 and C8. C5, C8 are chiral carbon. Chiral carbon. Because of this chiral carbon, it will show optical activity. So we saw that it is dextrorotatory. We saw that. That is the one point. And C9, C10, C9 and C10 we have double bond like this, C9, C10, which is in conjugation with this, right? So this is the structure of lysergic acid and this is the structure of isolysergic acid. So in presence of base, this reaction happens. So these things they will ask in the exam. So you please remember these things, right? So once we understood this, let us see one more reaction which is very important, right? So now we give the position of this conjugation. We told we give the position of COH. We told the tautomerism in which lysergic acid is converting into isolysergic acid in presence of base OH minus. So all these things we have studied now. Only now I have to give the position of this tertiary NCH3. How did it come there only? What they did, they took this lysergic acid, they treated with this acetic anhydride, I guess. Let me check it. Yeah, it is acetic anhydride only. No. Acetic anhydride. They took this acetic anhydride and they heated and they found that it formed lectum. What is this lectum? Lectum is nothing but, see, this is ketone, right? Cyclic ketone we call it as lactone, right? And this is what? This is amide. If I have cyclic amide, we call it as lactam, right? So what is this cyclic amide? How it formed? So if you now we know this structure of this lysergic acid, only last ring I will write now. So this is my last ring. I gave the position of NCH3 here, and above the plane I have this COH group here, COOH, and here I have double bond. Other three will be as it is, right? So this is the structure I had, right? And here I have this is this hydrogen is there, right, which is below the plane. That is acidic in nature because it is present on alpha carbon to this electron withdrawing group, right? So whenever I have acidic acid, AC2O, its structure is AC means CH3CO and one oxygen is there, another molecule of CH3CO, CH3CO, CH3CO and one oxygen. So it is called as AC2O, right? So this is the structure. So here I can if I break like this, I'll get O minus like this we will get, right? So this O minus can take this acidic proton like this. So as soon as this acidic proton goes, this electron density, right, it comes on here, this carbon-carbon bond, this bond will be broken and electron density comes on this nitrogen. So N minus, that N minus will take this proton. So it is like tautomerism only. Here the tautomerism happens in presence of acidic acid. So what happens? See here. Other thing remains as it is. And here I have COH group. And now this bond is broken, carbon hydrogen, and we got double bond here. And this bond is broken, the negative charge here CH3 is there, negative charge came on nitrogen. Right, here proton is H plus. That H plus and this nitrogen can react to form NH. Right, so this is the thing. Further what happens? See, this is what carbon-carbon single bond is there. So it can rotate. So if I rotate this carbon-carbon single bond, what I will get? I will get this thing. See here, N, H, CH3 and I have double bond here, single bond. Now this double bond goes here and I will get COOH here, right? So this reaction, I am heating this reaction in presence of acidic acid, I am heating it, right? So as I am heating this reaction, what happens? This nitrogen amine will be having lone pair, so it will give its electron density. This OH minus is good leaving group, OH minus, and this H plus will be removed and it will form water molecule. So while heating, I will get water molecule. So what happens here? 1, 2, 3, 4, 5, 6. This carbon 1, 2, 3, 4, 5, 6. 6-membered ring formation was happening. Right. So this is the 6-membered ring formation, in which it found C double bond over here. Here I have CH3. This hydrogen will go out to make this nitrogen stable, that is neutral. Other thing, double bond here, one double bond, and other double bond is here. Right. And here I had conjugation, right? This way the bond is there, other bonds, other substitutions, other ring and indole ring, everything that is there below. Right. So we used to get this cyclic amide. This is amide, right? CONH. So here it is CONCH3, right? So this is cyclic amide, that we call it as lactam. Right. So this lysergic acid, when heated with acetic anhydride, will get lactam. So this is the reaction. So these reactions they will ask in your exams. So you need to remember all these reactions, right? So I have done with the thing. If they ask in exams, you should draw the full complete structure of this lysergic acid. Here I have made this wavy arrow. It means it is in continuation with other ring, but you should draw it, right? So based on all these reactions, formation of lactam, they give the position of NCH3. It will be like this only. COH group will be here. And also I told this is also kind of tautomerism, and with OH minus their tautomerism is also little different. There the H plus will go here, right? Here we will get double bond, but here what happened? Ring breaking is happen. Here we will get double bond and ring has broken here, right? So this is the thing, right? So these are the few reactions I wanted to tell, and we concluded that this lysergic acid has got the structure as like this. So now you should be able to draw the structure of lysergic acid. So it has got indole skeleton like this. Here NH is there, and here 1, 2, 3, and here we have 6-membered ring, and above one more 6-membered ring. Here nitrogen we have, which is tertiary CH3, it is attached, and here we have conjugation like this, and double bond I have here. If COH is above, then we call it as lysergic acid. Same structure, same indole, everything. So this is the nitrogen which is secondary, and if COH is below like this, then it is isolysergic acid, and conjugation is same as it is. Here we have nitrogen which is CH3. So they will show tautomerism in presence of OH minus, that also we have seen, right? So these are the things we have studied. So now you know the structure of lysergic acid, right? Here this COH group will be above and this COH group will be below. Means the difference between lysergic acid and isolysergic acid, the stereochemistry at C8, here the stereochemistry at C8 will be different. Here also we have stereochemistry. This is also chiral carbon, this is also chiral carbon. That carbon is C5, but it will be having same. The stereochemistry what this lysergic acid has, the same stereochemistry this isolysergic acid will have. So these things are same, but only the stereochemistry at C8 position is changing. Here COH group is above and here COH group is below. So this is about lysergic acid. I hope you enjoyed this video. In next video, let us synthesize this lysergic acid. How they synthesize it in lab, that we shall see in the next video. If you like this video, please give me a like button, share with your friends. If you are not a member, become a member by subscribing it. Right? Thank you.